Welcome to 40th lecture on electrical machine 1 course, and we have started discussing on 3-phase transformer as a single unit. And in our last class I told you that you take 3 single phase transformer. Imagine that you have taken 3 single phase transformer and you have joined the one of the limbs of each of them together, and then the secondary winding you put on the outer limbs, and then the flux in this central limb, instantaneous value of the flux will be 0, because phi A, phi B and phi C they are 120 degree out of phase. So, that material can be avoided, and still the structure is somewhat awkward. So, a simplified way of making a bit of constructional features, that is in fact I am telling, is that you take plain laminations with 2 windows like this, like this. So, this is the lamination in one plane, and put several of them to get the height or the width of this transformer. That is, in 3 dimension it will look like this, which sectional view will be like this. So, there will be 3 limbs, and in each of the limbs you put coils of one phase, say A1, A2, and its secondary, instead of putting it some other place, we should not do it in case of 3 phase court type transformer, which is very easy to construct. And then you have its secondary, and these terminals will be marked as A1, A2. Similar is the case with B phase winding. You have several, its primary and its secondary, and they are B 1, B 2 primary, small b 1, b 2 secondary, and finally the C phase winding, C 1, C 2 and small c 1, c 2. Okay. And so, basically the analysis will remain same as that of a bank of 3 single phase transformers. That is the representation of this in terms of coil. I will show it similar to the previous one, A 1, A 2 and its secondaries, with the understanding that capital A 1 and A 2 they will be the dot terminals B 1, B 2, and this is small b 1, b 2, and this is capital C 1, capital C 2 and small c 1, c 2, and then I could connect them in star star, delta star, y delta and what not, with some specific vector grouping. Okay. But the only thing here one must understand that suppose you connect these 3 in star, and excite it with secondary open circuited, secondary also suppose star. So, this will perhaps give why perhaps it will give me y y 0 connection, but the point I want to tell you that with secondary open circuited, primary energized, the reluctance of the flux of phi A and phi B will be different, because the flux phi A will get divided like this into two parallel paths, sorry, phi A. Phi B will be like this, it will divide here itself in two paths, and phi C will be once again like phi A, it will be like that. Therefore, the reluctance may be different slightly. Therefore, the no load current required, magnetizing current required will be slightly different in the phases. Now, if you energize it with balanced 3-phase source, then one thing is clear, as I am repeatedly telling you. Suppose primary star connected. So, flux created by A phase phi A, its value gets fixed by this voltage, is not n d phi dt. Suppose these primaries are capital N 1. So, what is the value of phi A max A phase? That phase voltage whatever you have applied across capital A 1 A 2, that divided by root 2 pi f n 1. Similarly, if this voltage supply voltage is balanced, so this phi b will be also like that, its strength phi b, and phi c will be also like that, getting the point. Now, these three fluxes, as if we will presume they come here and meet, they vanish, because phi A, phi B, phi C are 120 degree apart, clear. But nonetheless, in the limbs, this limb it has to be phi A, in this limb it has to be phi B, because KVL is to be satisfied in the primaries and this is phi C. So, phi A, phi B, phi C perhaps will meet here and vanish, annihilate themselves, because they are 120 degree apart. So, things are expected to work, why not? Okay. So, this is the thing. Then you can proceed so far as connection is concerned with the understanding that these are dots. There is no difference in the making connection. So, like star star, delta star, star delta and so on with this transformer also. So, no point in repeating in that. But so this is called court type. There is another type of 3-phase transformer possible, that is called shell type. I will just sketch that shell type and write it like this, shell type. Here it is much more symmetric so far as the reluctance this dash is concerned, and the flux paths are independent. What they do is this, as if you have taken I will just mention this. Court type is much more popular, easier to construct, shape is fine, and this is the third one. This is the sectional view of the stampings. These are windows, this is the iron portion. Here what is done, the windings are placed here, primary, secondary. Similarly, this is for A phase. I am not going to mark the terminals, it will become too clumsy. So, this is for A phase, say I will take this color, and this is for say B phase, its primary, its secondary. and C phase, primary, secondary. Got the point? So, here you see how these flux paths will be there. This is, so you see the windings are placed on the central limb, not on the outer limbs. Okay? And the flux, if you energize the primary FS, it will produce phi here, it will nicely close onto itself. Getting the points. Similarly, for B phase, flux paths will be like this, as if they are independent 3 single phase transformers. In fact, they are, but only thing the windings are on the central limb, and here also C phase flux will be somewhat like this. But here the fluxes do not have that is, they interact phi A, phi B, phi C directly. That is why the no load current will be slightly different. So, this is called shell type. Oh, I have written. Anyway, in the cell type, some people say a cell type is that type of transformer where iron, similarly in the single phase transformer also you could have a, in fact, there are single phase 3 number of shell type transformers. You can make a single phase transformer in this way. In contrast with the coat type single phase was what? It was like this. Here is primary winding, there is secondary winding, and they may be put in the same limbs, distributed on both the limbs, primary, secondary, but effectively it is like that. Here the primary and secondary will be put here. Just get the idea, that is all. So, this is single phase cell type. People say that in single phase iron embraces the winding, in the coat type coil embraces the one, as you can see iron is outside. But anyway, operation etc. will be similar, flux paths will be different. So, this is shell type transformer, okay, 3 phase, of which this coat type is more very much popular, and they are used to make say power transformers all coat type. Okay. Now, after telling this, I must tell what about the nameplate rating of a, I will draw a vertical line and write like this, nameplate rating of a 3 phase transformer unit. It will be written as, suppose 30 kVA, say I am just giving some number, say 600 volt stroke 200 volt, which is not very practical numbers, but just I am giving you for easy computation, 600 volt, 200 volt, 50 hertz, and before that 3 phase 30 kVA, 600 volt, 200 volt, 50 hertz transformer. Mind you, it is not the collection of 3 single phase identical units, and this is the nameplate rating. Also, you will be provided with the connections. For example, it may be given as y d 1. That means, the high voltage side will be connected in star, low voltage side in delta, and I know how to connect them. So, henceforth what I will do, because connections once I have understood, I will just tell that okay, this transformer, the normal way of drawing star and delta connection I will do. Okay, the primaries are connected like this. Even I will not mark A1, A2, A3, A4. We know that whoever has connected, he has connected properly, so that you achieve this YD1. Similarly, the secondary is delta connected. So, it will be like this, is not, and connected correctly. Okay. Now, for solving problems this that, it is better you draw this, so that easily you can interpret the data. Now, what this 600 volt means? This 600 volt means that this is HV side, this is LV side, this you listen carefully. This means line to line voltage, mind you. Similarly, secondary side voltage, unless otherwise specified, which will never be, it is like that only, but still I am telling, if nothing is specified otherwise, this will be also line to line voltage. So, this is line to line, mind you, and this is also line to line voltage. This is very important thing to note. Not that this primary winding voltage rating is 600 volt or 200 volt. Okay. What about the current rating? I told you in a transformer KVA and voltages are given, current values are not explicitly specified. From KVA and voltage informations, you have to find out the rated currents of the winding. In this case, this 30 kVA is the total kVA, total kVA. Therefore, from the total kVA and line to line voltage, I will be able to calculate the line currents of the respective side, not the winding currents. For example, if I say if I call this is side 2, this is side 1, I will say this line current IL2 will be given by root 3 into secondary side line voltage, that is 200 volt, root 3 VLL into IL2 is equal to 30 kVA, and from which I will be able to calculate IL2. Mind you, this from this formula you will be able to calculate the line current of this secondary side. Similarly, primary side line current, that is IL1, neglect that no load current, which will be 5% of that rated. This is the rated line current of the secondary side. Similarly, rated current on the primary side line current IL1 will be equal to same kVA 30 into 10 to the power 3 volt ampere by root 3 into 600. Got the idea? Approximately how much it will be? These values. Anyway, you calculate, then tell me. So, these are the line currents. I will be able to in ampere, mind you. Okay. Calculate it. So, see this comes out to be 30, 10 goes, this is 2, 2 root 3 is 2 into 1.7, 1000 by 2, 500 about. This one, say approximately say 28 ampere or so, correct. 1000 by, I do not think it is more than that. So, these currents I will be able to calculate, I will write it down. Now, then one may ask question, what is the turns ratio of the windings? How to find out turns ratio? Turns ratio of HV and LV windings, or turns ratio per phase. If you are asked to calculate the turns rate, suppose the number of turns of the primary winding is N 1 and secondary winding is N 2, then I will say N 1 by N 2 will be how much? The voltage across this, which will be 600 by root 3 divided by N 2, line to line voltage is 200 by 200. This will be the turns ratio, that is 3 by root 3 is equal to root 3 here. Okay. 280 ampere, about 280 ampere, this will be. This is the HV side. So, LV side it will be higher and we will be able to calculate. So, the rated currents of the lines are known. Therefore, rated currents this can you calculate, tell me this fellow. Rated current of rated currents of around 840. So, this is around 840 ampere. So, rated currents of windings, it is not this 840 or 280, LV rated current, that is this current ILV winding, rated current will be, this is 840, therefore, that divided by root 3, because it is delta connected, so much ampere. Similarly, IHV winding rated current, that will be same as the line current. So, that is 280 ampere, getting the idea. Therefore, you must remember on the nameplate of a 3-phase transformer of a single unit, compact 3-phase transformer, no 3 separate transformers you have put together for connecting it to work it as a 3-phase transformer, not like that, a single unit of 3-phase transformer, whatever kVA is given, it is the total kVA. Whatever voltage ratings are given are the line to line voltages of primary and secondary side. So, from which directly you will not be able to say what is the turns ratio of the coils, unless it is same connection, that is star star connection, turns ratio will be same as line to line voltage. Got the point? Any mistakes? So, this point must be very clearly understood. On the other hand, when I was using 3 single phase transformers, the rating of each one is known, and then depending upon the connections we decided what should be the line to line voltages. that I have discussed earlier, you must refer to that. But so far as 3-phase transformer is concerned, this is how it will be, its rating will be specified. Okay. Unless once again I am telling the same connection star star or delta delta, ratio of this line to line voltages will be same as the ratio of the turns ratio of the transformer. Okay. So, this is how it is to be done. Okay. Let me correct it. So, this connection this will be 280 ampere, please. This is 280 ampere, sure, na? 1000 by it was 20 root 3, that is the mistake, and it was 84. Please correct that. I have no calculator, 84, and therefore, ILV rated current will be 84 by root 3, and this rated current will be 280 only, 28 ampere. Clear? So, given the ratings, you will be able to calculate everything, including the turns ratio of the coils. Achha. Now, I will tell you about another connection first, then I will discuss about when to use stars connection, delta connection on the high voltage LV side, etc. Those some points I will discuss. But before that, another connection I will discuss. So, now I know that so far as connections are concerned, only thing you will ask for, where are my primary terminals with polarity marking A1 A2 capital, where is secondary small A1 A2 and so on. Then you can connect it, and it is same for both the kinds. Now, another connection I will just tell, which is also very interesting connection, which is called zigzag connection. In zigzag connection, it is usually denoted by Z, like star Y, delta D, zigzag connection is denoted by Z. And why zigzag connection is necessary, that also we will discuss. But first, let us, for academic interest, let us try to see what this connection essentially means. At the end, it will turn out to be equivalent to star connections. Let me explain. Suppose, and it does not matter whether you are using 3 single phase units or a 3-phase transformer as a single unit. For example, to connect a zigzag transformer, you must have, for a particular phase, say I am drawing here, suppose 3 single phase transformers I have taken. So far I was telling this is the primary winding and there was one secondary winding, A1 A2, is not? And similarly another transformer with B1 B2, small B1 B2. But in this case, to carry out zigzag connection, for each primary phase you must have 2 secondary coils identical. This connection is very interesting, A3 A4, and I will say that all odd numbered terminals are dots. It means this. Similarly, for B phase and C phase, which I am not drawing, 3 single phase transformer. Naturally, if you apply a voltage phasor, if the voltage applied in the primary across this transformer A1 A2, on the secondaries you will have 2 separate, but equal length phasors of the secondary, because their number of turns are same N 2 N 2 and this is N 1, is not. If you excite it with some voltage, then same voltages will be induced. And this lengths will be equal. Therefore, to carry out zigzag connection, we must have for each phase two identical secondaries. In case of three phase transformers, it merely means that is, if I go to previous page, which I have already drawn. For A phase, I have drawn only small a 1 a 2, but there is no space to accommodate another coil. What I will do here is that this limb only I am sketching. Suppose I can also do like this. This is the primary winding A 1 A 2 and there will be two secondaries like this A 1 A 2 and A 3 A 4. And this I will do for B phase and C phase as well. That is, each phase must have two identical secondary coils. So that is the thing. Therefore, the connections will be, so now I will simply draw the coils to execute connection, for example, A 1 A 2. Now, there are now two secondary coils A 1 A 2 and small b 1 b 2. Then for B phase b 1 b 2 and it will also have two coils b 1 b 2 and b 3 b 4. And finally, it will have C 1 C 2 and small c 1 c 2 and c 3 c 4, with the understanding that these are dots, all odd numbers. I am sorry, this will be A 3 A 4. The arrangement is understood absolutely. Then what I will do? I will make it, suppose primary I have connected in star. Okay, so I will clean this portion. Now, I know what it is. Okay. Now, primary I will connect in star, a valid star. For example, I will connect short A 2 B 2 C 2 and give supply to AS, BS and CS supply, and these are the primary phasors. And this is A 1 which is same as AS. This is B 1 same as B s and this is C 1, lengths are equal, and this is your neutral A 2 B 2 C 2. Now, on the secondary coils I have not connected it anything, but I have now these voltages available to me to play with. What I mean by this, that is, I will then have on the secondary side these two voltage A 1 A 2 A 3 A 4. Similarly, I will have parallel to B 1 B 2 B 1 B 2 and B 3 B 4. and also I will have these voltages. C1, C2 and C3, C4, is it? 6 voltage phasors will be available to me, 2 belonging to each phase. Now, what is zigzag connection means? These 2 phases, 2 secondary coils, you connect them in series. Okay. The rule is these 2 coils, take this is suppose group 1, this is group 2, you say, take A phase coil and connect in series with either B or C phase coils in the second group. That is, you do not connect A1, A2 and A3, A4 in series, there will be mixing of phases. So, these voltages are this one A1, A2, of course, you can connect them in series, then it will be normal effectively a single coil of 2 N2 turns. See, this is N1, this is N2 and this is also N2, all of them are N2, 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 N1, N1. So, what you will be doing in a sense is that you will connect 2 coils in series and try to achieve the connection. So, one coil from this group, this is suppose group 1 and this vertical coils group 2. So, take one coil here and take either B or C, whatever will be relevant, that we will discuss. Similarly, B phase and other from this one, these 2 you go on connecting in series and to achieve some what is called zigzag connection. Okay. So, the question is what is to be connected and how? The whole idea is that, for example, I would like to connect the primary in Y, secondary in Z, I would like to connect. And here also it is like say 1. Zigzag connection, although it is not yet done, but I told you it will come effectively a star connection, that is most probably 1, let us see, okay, Y Z 1, effectively star connection, but 2 coils will belong to 2 different phase groups and at the end 3 terminals will be shorted. Therefore, whatever will be the neutral, just like star, this side there will be a neutral and from neutral to one of the lines if you try to go, you will encounter 2 coils in series belonging to 2 different phases. Okay. Now, if this is the thing, this is A1n, therefore, A phase from the secondary, if it is 1, suppose this is the secondary neutral, which one will become neutral I am not sure yet. Suppose it is neutral, this is the A phase of the primary and I am telling it is 1 means 30 degree lagging. So, what I will do? I will draw a line 30 degree lagging here. So, neutral to A phase on the secondary side must lag, this was my A1, this vertical line primary, secondary A phase voltage will lag the primary A phase voltage by 30 degree. Now, the question is how this phasor can be achieved. It can be achieved. See, this was A1. So, I must this phasor can be realized by bringing this A1 A2 here, and then you can easily see this phasor is parallel to C phase. Suppose I have decided in the outer coils it will be A1 A2. So, I will write here as C4 C3. See, this phasor is C3 C4 plus A2 A1 can give me this one. So, this is one phase voltage. Now, once you have drawn this, the result is obtained. B phase will be 120 degree apart from this line. So, draw a line here, and here I must expect some B 1 must come. How that B 1 will come? And this phasor can be broken up into this plus these. So, if it is B 1, okay, B 1 is available, this must be B 2, and who will provide me this phasor? It must come from some A phase. A1 A2 has already been used, now A3 A4 is remaining. So, A3 A4, got the point. And where will be my C phase? It must be horizontal. After this one, this is 30, this is 90. So, here it must come, and this voltage must belong to some C 1. So, what it should be? A 1, B 1, and this is C 3. C 1, C 1, C 2 is available, okay, fine. C 1, C 2. I mean, these lengths are all equal, please forgive me for this one. And this will be provided by whom? By B phase. B phase, one voltage I have used B 1, B 2. So, B 3, B 4, B 3, B 4. Therefore, effectively now after knowing this, I will come for connection. It will be, as I told you, sort of star connection, 3 terminals must be shorted. So, and I now know which 3 are to be shorted. So, A 3, B 3, C 3 are shorted. Then what I see? A 2 must be joined with C 4. So, I will take a piece of wire, and I will clean this now. That group 2 previously written will be there, na? That is the problem. Anyway, but it is being recorded. Acha, in the so this you take a piece of wire and connect here. So, A 2 is to be connected with C 4, connect it, and this will go to your load A phase. Similarly, come to the connection. So, this is over. A 4 B 2 is to be shorted. Where is A 4? A 4. So, A 4 and B 2 are to be shorted. It will be like this, and this will come as B phase terminal. Similarly, C 2 B 4 are to be shorted. C 2 and B4 are to be shorted, and that will come as your secondary C phase terminals. So, you can see this is called zigzag connection. So, zigzag connection is essentially a sort of star connection, 3 term. You must require 2 identical coils, you cannot do anything, and we have just discussed how it can be done. Now, the big question is what for all these things, that is there, but suppose I say you that okay, a transformer each phase has got 2 secondaries, then it looks like okay, this way also one can get a balanced 3 phase output voltage. Rule is you take one coil here, I specify the rule belonging to one phase A phase, then you see this coil is in series with C phase coil belonging to other phase, B phase coil in series with A phase coil, and mind you these are the dots, and C phase coil is connected to B phase, and you get this connection. More on these connections next class. Thank you.